Welcome to Chem 313, Lecture 2. In today's lecture, we are going to review the subject of acids, bases, and buffers, which you should have seen in other courses, but we need to review it for the purposes of this course because it's going to become very important. The reason it's going to become very important comes at the end of today's talk, where we're going to look at the relationship between pH and the electrical charge of a molecule. Now, last time in Lecture 1, we did a review of intermolecular forces. And there were 5 intermolecular forces that you needed to know. There was the London force, the dipole-dipole force, hydrogen bonds, ion pair or ion-dipole interactions, which are not the same thing, but they're related, and the hydrophobic effect. And we left off the last lecture by stating that because weak intermolecular forces dominate biochemistry, a small change in our environment can affect the strength of our intermolecular force. Well, one such thing that can change the strength of your intermolecular forces is pH. And we'll cover what pH talks about, what pH actually is in a moment here. So pH is important because it influences the charge on any ionizable molecule in water. And because all of our intermolecular forces all boil down to charge interactions, a change in pH can change the intermolecular forces of our molecules. So today I want you to understand the following things. This is a really difficult lecture for most people. Understand qualitatively what happens when an acid or base is added to water. Also understand qualitatively what happens when an acid or a base is added to a buffer solution. And then also understand why adding acid or base will change the electrical charge on some molecules. All right, let's review acids and bases. We're going to only talk about the Bronsted-Lowry acids and bases. So Bronsted-Lowry acids and bases, an acid is an H+ donor. H+ we call a proton. It's a hydrogen atom that's missing an electron, but since most hydrogen atoms are just a proton plus an electron, we can call these a proton. So an acid, according to the Bronsted-Lowry definition, is any substance that has a hydrogen that is not especially strongly attached to it. So there tends to be very weak covalent bonds to hydrogen in Bronsted-Lowry acids. A Bronsted-Lowry base is a proton acceptor. And one of the key features of a Bronsted-Lowry acid and base system is that you always have an acid and a base together. you never have a free-floating proton. So sometimes as a shorthand, we will just say that you're forming a proton in solution, but you have to keep in mind that that never literally happens. Your proton jumps from one molecule to another. So for example, if we were to take HA here, which is considered an acid, and mix it with water, what we end up doing is we lose a hydrogen and we form H3O+. So in this situation, water is acting as our base. Now, after the reaction has taken place, what are we left with? What we're left with is our acid molecule that has lost its proton. So that is now referred to as a conjugate base. And H3O+, which is what is left open after our conjugate, after our base accepts a proton, that's referred to as the conjugate acid. Now, you may ask, well, why do we call it a conjugate acid? Why do we call it a conjugate base? Because in some situations, this reaction is reversible, and in that case, the proton would be going from H3O+ to A-, in which case H3O+ would be acting as the acid, and A- would be acting as the base. So in other words, acid and base in the Bronsted-Lowry system is relative. So we can distinguish between strong acids and bases and weak acids and bases. So a strong acid or base, it dissociates 100%, which means that the reaction above goes to completion. So that means that if we take our HA molecules and mix it in a solution with a bunch of water molecules, then at equilibrium, we are not going to have any HA left over, assuming that we have excess water, which of course we always would. So that's the definition of a strong acid or a strong base. Another way that you can think of is that if you were to write out the equilibrium constant for this reaction, the equilibrium constant for a strong acid or a base would be very large. I don't want to say infinite because nothing is ever truly infinite, but it would be very large. Okay, so a weak acid or base dissociates only a few percent at equilibrium. So if we had a weak acid, the equilibrium would look more like this. So the key feature of a weak acid or a base is that at equilibrium, we have both conjugate base and conjugate acid present. Now, if you're talking about weak acids or bases, we can measure the amount of dissociation of our acid or base using pH. So we define pH as follows. pH is equal to the negative logarithm of H3O+. If you know the square bracket notation, and if you don't, I'm going to tell you right now, square brackets around a compound means the concentration in molar units. So 1 molar is equal to 1 mole of solute, H3O+ in this case, divided by 1 liter of solution. So why pH? So this lowercase p you can think of as minus the log of. So pH is negative log of our H plus concentration, but as we said before, that we never have free-floating H plus. It's always going to get picked up by water. So we define it as negative log of H3O plus concentration. Now, what that means is the following. Let's say we have a weak acid and water. And once we mix them together and the system comes to equilibrium, we will have our conjugate base and H3O plus. All right, the more this equilibrium lies to the right, that implies that at equilibrium, we will have a higher concentration of H3O plus, and therefore we will have a lower pH. And the reason it's a lower pH is because of this negative sign in front of the log. So for a given acid or base, a stronger acid will give more H3O plus at equilibrium, which means a lower pH at a given concentration of acid. And vice versa for a base, except in the case of base, a stronger base would give a higher pH. Now, what does this look like in the case of a weak base? Well, in the case of a weak base, let's call our base B. I'll put a lone pair of electrons on there to symbolize the fact that most Bronsted-Lowry bases pick up protons on lone pairs. And what we end up with after we reach equilibrium is BH plus, which is going to be our conjugate acid, and hydroxide ions, OH minus. So once again, if the equilibrium is farther to the right, that means we have a higher concentration of OH minus, which implies a lower POH. POH is the same, except it's negative log of OH minus. Now, a lower POH is exactly the same thing as saying a higher pH. And the reason for that is because the concentration of OH minus and the concentration of H3O plus are linked whenever you have a solution that's in water. And the reason they're linked is because of the fact that water can auto-hydrolyze. So water can act as its own acid and its own base. So what's happening here is that we have one water that is acting as an acid, one that's acting as a base, and so we end up forming H3O plus and OH minus. The equilibrium constant for this reaction, we call it Kw, and it's equal to 10 to the minus 14. If you take negative logs of these numbers, what this is saying here is that H3O plus times OH minus, that's our equilibrium constant, is 10 to the minus 14. This is our equilibrium constant, by the way, because water is a liquid, and you'll recall that you do not count liquids or solids in the expression for your equilibrium constant. Well, if the concentration of H3O times the concentration of OH minus is equal to a constant, let's take negative logs of each of these. Negative log of H3O plus negative log of OH minus now must equal 14. So I'm making use of the fact that when you take the log of a product, the log of A times B is equal to the log of A plus the log of B. And we got rid of the minus sign on the right because we're taking negative logs of both sides. So this is just a fancy way of saying the pH plus the POH must equal 14. So what this means is that if your OH minus concentration goes up, your H3O plus concentration must go down, and vice versa. So this is handy because this means that if you know the pH, you know the concentration of both H3O plus and the concentration of OH minus. Okay, let's do a simple calculation. I do not so much care that you guys are able to do numerical calculations for acids, bases, and buffers. I might give you a couple of problems related to that, but what I care much more about is that you understand what's actually happening. So I'm going to go through this calculation pretty quickly. Let's take the case of a strong acid. We're going to dissolve HCl in water. And because it's a strong acid, the reaction is not considered irreversible. It's going to go to completion. So what's going to happen is we'll end up with chloride ions and H3O plus. Okay, so we're going to dissolve 0.050 moles of HCl in 0.80 liters of water. And that's a pretty small amount of HCl, so we can assume that when you mix these two together, the volume will not change and the volume of solution will be 0.80 liters. So this means we end up with 0.0625 molar HCl. So that is going to be our initial concentration of HCl in our solution before the reaction takes place. And our concentration of H3O plus is going to be very low, on the order of 10 to the minus 7 molar because of the definition of Kw. And that's essentially negligible, so we can consider it as roughly 0. Now, what's going to happen at equilibrium is at equilibrium, all of our HCl is going to be used up, and we're going to have 0.0625 molar chloride and 0.0625 molar H3O plus. So that means that at equilibrium, H3O plus is 0.0625 molar, and therefore our pH is going to be negative log of 0.0625, which is 1.2. Now notice here, because this is a strong acid, and the same thing would be true for a strong base, the concentration of acid or base initially, right, before the reaction takes place, is equal to the concentration of H3O plus or OH minus at equilibrium. In the case of a monoprotic acid or a base. If you have a diprotic or triprotic that can donate multiple protons, then it would be a multiple of that. So this is not the case for weak acids or bases. All right, so let's consider the same situation, except this time we're going to use a weak acid, HF. Now we've got a reversible reaction. So initially, once again, 0.05 moles dissolved in 0.8 liters of water, assuming that that doesn't expand the volume of your solution, which it probably won't, will have 0.0625 molar HF before any reaction takes place. However, this time, our reaction is not going to go to equilibrium. Our change is going to be some minus X, and we're going to develop some amount plus X of fluoride ion and H3O plus. So at equilibrium, we will have a certain non-zero amount of HF, and we will have X amount of F minus and H3O plus. So now the question is, how do we solve for X? Well, in order to solve for X, you need more information. We need to know what is the equilibrium constant for this reaction. Right, so that extra information we need is Ka. So Ka is the equilibrium constant for dissociation of a weak acid or a base. So for equilibria of this type, we simply call the equilibria Ka if it's an acid. There's also Kb's for bases, but Kb's are rarely used. In practice, we just talk about Ka's with the understanding that the reaction can reverse itself, in which case we would have to invert our equilibrium constant. So as long as the value of your Ka is known, then you can use it in the balanced equation for your acid or base dissociation, and then you can calculate how much conjugate acid, hydronium, and conjugate base are present at equilibrium. This is typically something that's going to have to be given to you. Now, what's actually more useful than Ka's are pKa's. And once again, if we use our P notation here, pKa is negative log of Ka, right? So a pKa is going to be a constant for a given acid or base. It is not like pH, which is a variable. pKa is a constant. A higher pKa implies a weaker acid or stronger base. A lower pKa implies a stronger acid or weaker base. So let's say, for example, that the pKa of this reaction up here is 6. What is that going to tell us? We're going to see what that means in a couple of slides here. So I'm not going to spoil the surprise for you just yet. However, pKa values for weak acids and bases are going to have pKa's ranging from about 1 to about 14 is the typical range. Anything outside that range is going to be a strong acid or a strong base, and we don't really deal with those in this class. Now, something else to notice about Ka's and pKa's is that Ka has units of concentration. So what that means is that if your hydronium concentration is equal to your Ka, then what that means is that your HA and your A minus concentrations are equal. Okay? Or another way of thinking of that is that if your pH is equal to your pKa, then your HA is equal to your A minus. We're going to come back to this point later on. All right, now let's forget about Ka's and pKa's for the moment, and let's just imagine in your mind pictures of molecules reacting together in a beaker or something like that. Let's say that we're going to add some strong acid to water. So I've got a container with a bunch of water in it. And I'm going to add a strong acid to it. What's going to happen? So what's going to happen is the following. We'll still have water, because we always have excess water. Water is always present in excess. But we're also going to end up with some H3O plus and some X minus. The reason for that is because our acid, HX, is going to react with the water by donating a proton. Normally, a curved arrow means you're moving electrons. I'm doing kind of a blasphemous thing here, and I'm moving a proton. So, you know, if you're an organic chemistry stickler, please don't sue me. All right, so what you'll notice here is that all of our HX becomes converted to H3O plus. Now, let's do the same thing. Let's add a strong acid to a solution, but this time it's not going to be to plain water. We're going to add it to a mixture of a weak acid and its conjugate base. So what I mean by a weak acid and its conjugate base is that you could have these compounds together in solution, and there would be an equilibrium that looks like this taking place. So we still have plenty of water. But we've also got a fair amount of HB and some B minus. And then we are going to once again add strong acid to this mixture. And what's going to happen? We have water. We have our X minus counter ion. But do we have H3O plus or not? Well, the answer is we are going to have some H3O plus, but we're not going to have as much as we did in the first situation. And the reason for that is because instead of the HX donating its proton to water, what's going to happen is the HX and the B minus are going to react to give us conjugate acid and X minus. So in this case, only some of our strong acid ends up as H3O plus. And the reason for that is because of this side reaction taking place with our conjugate base. If we had added a base to this solution, we could have a similar reaction taking place with the HB conjugate acid in our mixture here. So the question we have now is which of these two solutions, the top or the bottom solution, undergoes a larger change in pH when we add acid to it? Well, up here, remember, all of our acid ends up forming hydronium. So we have a large increase in our H3O plus concentration, whereas down here only some of it did, so we have a smaller increase in H3O plus. And this means that when we add our acid to plain water, we have a larger change in pH than we do if we have a conjugate acid-base pair. So let's demonstrate this graphically. So what we have just shown is the principle of buffering. And this slide is going to show you guys the idea of buffering. So let's start off in our simple situation here where we've just got water, pure water by itself. If we add a strong acid to it, what's going to happen? All of the H is going to go onto water, forming hydronium ions, so that we have a large change in pH. In this case, it would be a drop in pH. Alternately, if we added a base, the base would pick up a proton from water. And what we would end up forming is a bunch of hydronium. So in this case, we would have a large rise of pH. All right, so let's consider the situation where instead of water, we have water plus a weak base. Now, if we add acid to a solution of water plus a weak base, what's going to happen is that much of our strong acid will react with our weak base to give us a weak acid and a counterion instead of H3O plus. So we still get an increase in H3O plus, but it's pretty small. Therefore, we get a small decrease in pH. And the reason for that is that the A minus absorbs the protons, not water. However, if we were to add a base to this solution, we would not get the same effect. So notice if you add a base to this solution now, all of our base molecules will take a proton from water, and therefore we have an increase in our OH minus concentration, and we have a large change in pH. But now let's imagine a situation where we have both HA and A minus together in solution. Now if we add strong acid, we will end up forming more HA and we only increase our concentration of H3O plus a little. And likewise, if we add a base, we end up forming just a small amount of OH minus and more BH plus. And so here we also have a very small change in pH. And so if we have both a weak acid and a weak base together, we have a solution that is resistant to changes in pH. So now we're finally at the situation where we can formally define what a buffer is. A buffer solution is a mixture of a weak acid and its conjugate base, and for a buffer solution to work, the HA and the A minus must be present in similar amounts. And this resists changes in pH caused by an added acid or base. Okay? So when I say HA and A minus, I'm saying that HA is the weak acid. A minus is its conjugate base. But a point I want to make here is that the conjugate base is also going to be a weak base. So I know if you think back to Chem 126 and 129, they teach you, oh, well, the conjugate acid of a weak acid is a strong base, and the conjugate base of a weak or a strong acid is a weak base. The whole point here is that it's all relative, right? So if you have a fairly weak acid, then your conjugate base will be a stronger base than the acid was in acid. But they're all still weak acids and weak bases. It's just there's relative degrees of weakness and strongness. All right, remember that. So buffers resist changes in pH caused by added acid or base. There is a formula that allows you to calculate what the pH of an acid or base solution is based on the concentration of conjugate acid and conjugate base if you know the Ka. This is what's called the Henderson-Hasselbalch equation, and I'm going to present it here without deriving it for you. However, I urge you to do practice problems so that you can get comfortable doing pH calculations using this equation. There's always going to be one or two of those in my class for credit. So the idea here is that we have two variables, the concentration of our conjugate acid and the concentration of our conjugate base. These you can control to some extent. Our pKa is a constant. Our pH is a dependent variable. So what this means is that if we have a higher ratio of conjugate base to conjugate acid, then that means that we are going to have a higher pH. Now, typically the way this works in a lab setting is you can choose the pH that you want, and the way that you would do this is by choosing a weak acid or a base pair whose pKa is close to the pH that you want. And the reason that that works we'll get to on the next slide. So there's something that's worth noticing right here, and that's what's down here at the bottom. If you're in a situation where the concentration of conjugate acid is greater than the concentration of conjugate base, what does that mean? Well, that means that our ratio on the right-hand side is going to be less than 1, which means that the log of that is going to be negative, and therefore our pH will be below our pKa. And vice versa, if your conjugate acid concentration is less than your conjugate base concentration, then everything is reversed and the pH is going to be above your pKa. Another way to think of this is that if our pH, which after all is a variable, rises above the pKa of our weak acid, then the concentration of our conjugate base will be greater than the concentration of our conjugate acid. And the more it rises above pKa, the bigger this inequality will be. All right, so before we go any further talking about how buffers work quantitatively, we need to get some definitions out of the way. A lot of times you'll hear me say concentration of buffers. So for example, we'll say something like a 0.50 molar phosphate buffer. What do we mean by that? What we mean by that is that the concentration of a buffer is equal to the sum of the concentrations of the conjugate acid and the conjugate base. So for a phosphate buffer system, it depends slightly on the version of phosphate that you're using, but usually you have what's called a monobasic phosphate, which is your conjugate acid, and you have a dibasic phosphate, which is your conjugate base. And therefore, a 0.50 molar phosphate buffer would be one in which the sum of this and this adds up to 0.50 molar. Notice also that I've written HA and A minus just by convention the way most textbooks do it, but the charge of the two doesn't necessarily have to be neutral and -1 respectively. So in this case, your HA has a -1 charge and your A minus has a -2 charge. So your conjugate base will always be more negative than your conjugate acid, but it isn't necessarily going to be 1-. There's another term called buffering range. The buffer range is the pH range in which the buffer resists changing in pH when acid or base is added. Keyword is resists. It doesn't completely avoid changing pH, but it doesn't change by very much. Typically, this is between 0.1 and 10 of your ratio, or pH is equal to pKa plus or minus 1. We'll see how that works on the next slide. The next term to know is buffer capacity. Buffer capacity is the number of moles of acid or a base that you can add without pushing the pH out of the buffer range. And this depends on the buffer concentration. So the buffer capacity is always proportional to the concentration of the buffer. And it's going to be different at different pHs. So it also depends on pH to some extent. Okay, let's look at the pH dependence in a buffer solution. This is essentially a titration experiment. So what we have on the y-axis is pH. This is what we're going to be measuring. And on the x-axis, we have the ratio of conjugate base to conjugate acid. So you can imagine that we have this acid and base system together. Sorry, that should be water. And let's say that we're going to add some strong base to our solution so that the base can react with our conjugate acid, giving us a conjugate acid and more A minus. So as base is added, our concentration of conjugate base goes up, and our concentration of conjugate acid goes down. Therefore, the ratio is going to go up. So if we were to do this experiment, if we were to start off with a solution that starts off at all HA and no A minus, and then at very high ratios we have all A minus and no HA, and we were to measure pH throughout this whole transition, what we would see would look something like this. We would have a curved line that sort of flattens out at some intermediate situation, at some intermediate ratio. What you would notice is this. The inflection point here, so the flattest part, occurs at the point at which A minus over HA is equal to 1. So in other words, we have equal amounts of conjugate acid and conjugate base. And if you were to trace over to the pH axis, you would find that at this point, the pH is equal to the pKa of our conjugate acid. So what do you notice from this curve? You'd notice that our pH curve is flattest when the pH is close to the pKa. If you get very far above or below that, then the curve starts to get steeper. Now, let's say that we continue this experiment and we're going to add more base. Let's say we start off at exactly equal amounts of acid and base, and we're going to add more base. Well, once again, as base is added, we're going to be consuming our conjugate acid and we're going to be forming more conjugate base. So our ratio is going to increase. So adding base pushes us up in this direction on our titration curve. And eventually we will reach a point at which our A minus over HA ratio is equal to 10. If you were to follow that over to the pH axis, you would find that the pH is equal to the pKa plus 1. That's due to the Henderson-Hasselbalch equation. And what do we notice at this point where the A minus over HA ratio is 10? We notice that now our pH curve gets steeper. The same thing would happen if we added acid. We would finally reach a point at which the ratio is equal to 0.1, and at that point, our pH would be equal to pKa minus 1. And here the curve steepens again. So the pH curve is going to be the flattest when we are near pKa is equal to pH. Whenever the pH is equal to pKa plus or minus 1, that means that our A minus over HA ratio is somewhere in the range of 0.1 to 10, and that means that we have some of both of our conjugate acid and our conjugate base in solution. And as long as you have some of both, your solution will be able to resist both acid and base. If you get outside that range, then you're going to lose your ability to resist changes in pH. This is why the buffer range is pH equal to pKa plus or minus 1. If your pH value is more than 1 pH unit above your pKa, you will not be able to resist changes in pH caused by added acid or base. Now, I am going to assign you guys some practice problems. I say you're going to want to see homework 1 and also worksheet 1. But I don't so much care about numerical problems in solving buffers. What I care about, the reason we care so much about pH is the relationship between pH and the electrical charge of certain molecules. So here's the thing. Many molecules, whether they're in a buffer solution or not, can act as weak acids or bases. All right, so for an example, I'm going to give you this molecule, PNP, paranitrophenol. So paranitrophenol is a weak acid. It's a weak acid because in the presence of water, it can donate this proton right here to give us H3O plus and a conjugate base. So anytime that you have a weak acid, you have a pKa. What do we mean by that? What we mean by that is that as long as a reaction such as this can take place, we have an equilibrium constant Ka, and our pKa is simply the negative log of that equilibrium constant. So for the case of PNP, our pKa is, I believe, 7.8. Okay, big deal. What does that tell us? Well, it tells us something that's rather important. So remember, solution pH is variable. So that means that if our pH is less than 7.8, that means that our concentration of conjugate base over conjugate acid is less than 1. Or in other words, we have more conjugate acid in solution than we have conjugate base in solution, right? So for example, if we were in solution at a pH of 5, that means that we would have a lot of the protonated weak acid form of PNP and very little of the deprotonated conjugate base form of PNP. What do you notice is different about these two molecules? What's different about these two molecules is that one of them is missing a proton, which means that if it misses a proton and leaves its electron behind, you're going to gain a negative charge. So that means that at pH 5, PNP is predominantly neutral, because this is the dominant form in solution and it doesn't have any net electrical charge. And that's true at any pH value below 7.8. But at any pH above 7.8, right? So let's say that we change our pH from pH 5 to pH 10. Now we're going to have very little of our protonated version and lots of our deprotonated version. So at a pH above 7.8, PNP is predominantly negative. So this illustrates an important general point for us. For in any molecule with titratable groups, and by titratable groups I mean that they can gain or lose a proton, as pH goes up, the net electrical charge on the molecule becomes more negative or less positive. There's another formulation that I think is more useful if you're looking at individual molecules. As the pH in solution rises above a pKa, your molecule either gains one negative charge or loses one positive charge. And vice versa, as pH drops below a pKa, molecule is going to either gain one positive charge or lose one negative charge. Now, there's an important thing to understand here. We are talking about on average. It's not as if every single molecule of P is neutral at pH 7.7999, and when you raise the pH up to 7.8001, every single molecule is negative. It doesn't work that way. We're talking about populations here. The pKa you can think of as a pH tipping point. It's where the population of your molecule goes from net one charge to net another charge. And because electrical charge influences intermolecular forces, this is why we care so much about pH, and this is why we like buffers. Because if we can control our pH, then we can control our intermolecular forces. Things get a little bit more complicated when you start talking about polyprotic molecules. So polyprotic molecules are molecules that have multiple titratable groups. So for example, molecules we're going to see later this week are amino acids. These are polyprotic as a rule. So for polyprotic molecules, here's my advice. Learn the structure and the charge on your molecule at one pH value. And then if pKa values are given, you can figure out the charge at other pHs. Worksheet 1 has a problem related to this. So in any polyprotic molecule, if you have multiple titratable groups, you're going to have multiple pKa's. So as an example, I give you tyrosine, which is one of our amino acids. What I'm going to do is I'm going to show you the structure of the molecule at a pH of 7, which is close to what plain water would be. At a pH of 7, tyrosine looks like this. So this is something you simply have to know or be given, what the structure of the molecule looks like at a certain pH. But the nice thing is if you know what the pH is and the structure at that pH, and you know what the pKa's are of the titratable groups, you can figure out what the structure and the charge on this molecule would be at any other pH. So typically what would happen is I would give you pKa values. So tyrosine has 3 tritratable groups. This one up here, this one here, and this OH down here. The H3N plus group has a pKa of about 9.5. The COO minus group has a pKa of about 2.5. And the OH has a pKa of about 10. So let's say that we start off at pH 7. And we are going to add some base so that we end up with a solution that is at a pH of, let's say 9.8. So what is going to be the structure or charge at pH 9.8, the predominant structure or charge? Well, what's our charge at pH 7? Well, we've got a 1 plus charge right up here. We've got a 1 minus charge right there. So our charge is going to be 0. It's net neutral. Okay, let's raise the pH to 9.8. Now, whenever you raise pH, if you raise pH above a pKa, that means that group loses a proton. And if you drop pH below a pKa, that group gains a proton. This is why when you go down in pH, your molecule becomes more positive or less negative, and vice versa when you raise pH. So if we're going to raise the pH to 9.8, we have to ask ourselves which groups have pKa between 7 and 9.8. Any group on this molecule that has a pKa value between 7 and 9.8 will change when we raise the pH. So what do we notice? Well, we notice that our amine has a pKa of 9.5. That means that when we raise our pH value, it's going to lose a proton. So at pH 9.8, our molecule of tyrosine will predominantly, not every last molecule, but predominantly look like this. And at that pH value, the proton that used to be on this amine would go to water. So what's the charge on this molecule? Well, now we've lost our positive charge, but we still have the negative on the carboxylic acid. So our charge is now 1 minus. If instead of adding base, let's add more base and go up to a pH of 11, now what's going to happen? Well, if we go from pH 7 to 11, we have to ask ourselves which groups have pKa values between 7 and 11. And the answer is 2 of them do. We have the amine group that we already talked about, but also the OH group that we talked about previously. So at pH 11, our molecule would predominantly look like this. And now our charge is 2 minus. So we can summarize by saying that whenever a pH rises or falls above or below a pKa, the net charge on our molecule will change. As you go up in pH, the molecule becomes more negative or less positive. And as you go down in pH, your molecule becomes more positive or less negative. I refer you guys to the homework and the worksheets for practice problems related to this subject. It's absolutely critical that you understand this relationship between pH and electrical charge, because this explains why when pH changes, so do the intermolecular forces acting on these molecules. For example, at pH 11, our tyrosine is going to be very negatively charged, which means it's going to be more strongly attracted to a positive ion than it would be at a pH of 7 when it has a neutral electrical charge. We'll talk about this topic more as it pops up in the context of real biomolecules throughout the rest of the quarter.